So a neat, if not a bit science fiction-y application of centripetal force would be the idea of a space tube or some sort of interplanetary craft that used a spinning cylinder in order to simulate gravity for the people who live inside of it. So the idea here is if you were to try and live in a spaceship, or like if you see the shuttlecrafts or if you see space stations that we have now, the people who are in them float all about. And not only is that a touch disorienting, but it also has some effects on your physiology, right? When astronauts return, their bone density has dropped because their skeletons are no longer under stress. So they start shedding calcium, which is problematic, especially if you plan to land on a planet at some point after your long interstellar journey, well, even interplanetary journey. And while it looks like astronauts are having a lot of fun zipping around, drinking juice that forms little bubbles and trying to work on stuff that keeps floating away, there are also issues with having to engineer a toilet that works under zero gravity conditions. And while it looks really fun to sort of float off your bed in the middle of the night, I don't think they actually have to like seat belt themselves into bed to go to sleep. And I don't know about you, but relaxing in my straitjacket at the end of a hard day's work doesn't sound like a lot of fun. And considering that the trip to Mars is like, what, 3 years, having to straitjacket yourself to sleep every night for 3 years probably has some psychological consequences. So it would be nice if we could just go to bed at the end of the night and have our juice stay in a cup, so that we don't have all these complications to deal with on what is already a complicated feat of flying from one planet to the next. So if we assume that the average person is 2 meters tall-ish, then we're going to need a room that has a radius of at least 3 meters so that we can walk around it. So I'm just going to draw that here. It's a radius of 3 meters. And what I'm going to do is I'm going to let this thing spin. Around and around and around and around. So the fun part about this is maybe you're here, and maybe your roommate is over here, and I don't even know what to draw over there, so I'm just not going to. And your cat is sitting over here with you. The idea is that if I've got this spinning at the right rate, then you should be able to stand on the inside of it and feel a force outwards from the center of this can. So what's actually happening is it's your body trying to fly off of the circular path, and the material of the spinning can is holding you back. It's forcing you to orbit the center of this rotating can. So you can imagine what life like this would be like, right? You have a wrench or something, you need to hand it to someone who's standing beside you, so you hand it to them like this, because they're standing up there, which would be a touch disorienting, but better than straitjacketing yourself to sleep every night. So the question is, how quickly would I have to spin this tin can with a radius of 3 meters in order to have it feel like I'm experiencing gravity while standing on the inside of this can? Well, you've got a centripetal force equation, which is Fc equals mv squared over r. And the centripetal force I want to experience is gravity. So I want to equate this to mass times 9.8, so that this spin force is simulating gravity on Earth's surface. Well, if you notice, the masses cancel out. That's good. So v squared would be the radius I'm trying to go at multiplied by g. And so v squared then would be the 3 meters multiplied by 9.8. And so v would be 3 times 9.8 is 29.4. And if I square root that answer, I get 5.422 meters per second. Which is, in kilometers per hour, 19.52 if I round. So that's not a crazy speed. It's also, if you've got a mind for ridiculous engineering feats, this is also implying that if the can was not rotating and you were instead on a motorcycle traveling at 19.52 kilometers an hour, which is not ridiculous on a motorcycle. In fact, you could ride a normal bicycle at that speed. You should be able to ride around and around and around on the inside of that thing without falling off, which is kind of neat. That's not a crazy speed. We could get that going. If I wanted to phrase this instead of a tangential velocity, if I wanted to change it to a period of rotation, I just have to remember that speed is distance over time, and the rotational period would be a circumference, 2 pi r for one full rotation. So 5.422 equaling 2 pi times 3 over t. Pop the t up here. 6 pi over 5.422. 6 times pi is 18 something divided by 5.422. Gives me 3.476. So as long as this can makes a full rotation every 3.476 seconds, then your feet will be experiencing a centripetal force that exactly replicates the force of gravity they would feel on the surface of the Earth, which is a neat little trick, because all you need to do is spin your shuttlecraft, and then you don't get gravity, but you get something that feels like gravity. And that solves a whole bunch of sort of lifestyle issues for the people who are trapped in your tin can hurtling through the darkness of space. Teeny tiny complication. If we build a tube like this, so it's only 3 meters in radius or 6 meters across, where's your head? Well, if your person is 2 meters tall and the radius is only 3 meters, then the top of your head, or where your face is only 1 meter from the center. So what's happening 1 meter from the center? What's happening to your head? Question mark. Well, just using the centripetal force equation again, Fc equals, well, your head has a mass, and I could do v squared over r, or I could use that other version of the equation, 4 pi squared mr over t. So I have a radius, and I'm just going to leave the m unknown, and I have a time, right? Because your head is making the same, it's making this full rotation every 3.476 seconds, the same way that your feet are. But your head isn't traveling as quickly because it doesn't have as far to go. So that's why I'm not using this version. The speed, I'd have to recalibrate my speed to use this version, so I'm just going to use that one. So I have 4 pi squared. The radius is 1 at my head. The orbital period is 3.476. I'm just going to write this mass over here. So 4 times pi squared gives me 39.478 divided by 3.476 equals 11.357. That's not right. Sorry, there's a square down there that I forgot. So 4 times pi squared gives me 39.478 divided by 3.476 squared equals 3.267 m. All right. So I don't know the mass of your head, so I don't have anything to put in here, which is a bit problematic. But fortunately, I'm really only concerned about comparing it to gravity. So what I'm going to do is I'm going to take this force, this centripetal force, and you're going to write it as a ratio to the force of gravity, which is 9.8 multiplied by your mass. You notice that the mass is divided out. So if I do this little calculation, I'm going to put it on this side so it doesn't end up on my face. That number divided by 9.8 gives me 0.333. So what? Well, the ratio between the centripetal force and gravity at your head is only 33%. So in a machine like this, while it's spinning, your feet are experiencing gravity as they do on Earth, but your brain is only experiencing 33% of gravity, which is bad because there isn't as much gravity pulling the blood back from your brain. So you're going to end up with some interesting circulation going on in your vessels. So you can sort of see why this isn't done at this point, because spacecraft are about radius 6 meters. That's 20 feet. They might be a little bigger than that, but they're not 10 times that big. Once you're getting into something the size of the International Space Station, sure, you might be able to get away with this, but the dimensions on the space station are the lengths of the solar panel arms. They're not the width of the tube that people live in. So while this is a cute little idea to come out of a high school physics class, how big would this have to be in radius before you didn't have this problem? So how big am I going to have to make this tube so that this replication of gravity through centripetal force is actually practical without creating a huge gradient between the top of your head and the bottom of your feet? Well, I can do that. I just need to do some algebra. So I'm going to clean her off and I'm going to see what happens. All right, so here's our setup. I have a very large cylindrical can that I'm going to start spinning. And I want your feet to experience 1 g worth of force. I want the very tip top of your head to experience 95% of Earth's gravity. And we're going to say that you are, or most people, the standardized convenient unit human being is 2 meters tall. Okay, so I'm going to use an R for this radius, and then this line here would be whatever this radius is, subtract 2. So at R equals radius, I want FC to equal mg. Radius equals the arbitrary radius less 2 meters, I want the centripetal force to equal 0.95 times the force of gravity. So I'm going to fill all that stuff into this thing here. So mg equals 4 pi squared mr. Oh, yeah, because the r we're using is r over t squared. And over here, 0.95 mg is equal to 4 pi squared m, and the radius I'm using is r minus 2. All right. Now, by interesting algebra trick, m is divided out on both sides. I'm going to pop the t squared up on both sides. And I'm going to put this 0.95 down here. Okay, now the idea with the space tube is that as you go, it takes the same amount of time for your head as it does for your feet to take one full rotation. So this time and this time match each other, as does g. So this equation then must equal that one. So I should be able to hook them together. And that would give me 4 pi squared r equals 4 pi squared r minus 2 over 0.95. All right, again, through interesting algebra, the 4 pi squareds divide away, and I can pop my 0.95 up there. So I just have to gather some like terms. I'm going to bring the 0.95 over here, and I'm going to kick the 2 over to that side. One r minus 0.095 r's is 0.05 r's. That is an n, not an r. So 2 divided by 0.05 equals r. So the radius would need to be 40. All right. So if this radius, the radius of my can was 40 meters, and I spun it fast enough so that your feet were experiencing 1 g worth of simulated gravity, then your head, 2 meters above that, would still be experiencing 95% of Earth's gravity. So that's not such a gradient through your body, which might make this actually possible. If you think about that, though, a can with a radius of 40 meters is 80 meters in diameter. So this is a cylinder that is almost as wide as a soccer field. That's quite a vessel. An aircraft carrier isn't that wide. So to pull this off would be quite a feat of engineering because it would be so large. But would it be worth it, making a ship that you could actually walk around in instead of having to float everywhere? And I know I keep saying this, but it really deeply traumatizes me, the thought of it. Straitjacketing yourself into sleep every night. All right. Well, we've got a radius. We might as well work out the speed, because that'll be the second limiting factor. If I have to spin this thing at 7,000 meters per second, then it's not going to work. So at that radius, in order to simulate 1 g worth of force, what would the orbital period be, and how fast would it be going? So I'm just going to clean this off here. I just need to grab my centripetal force equation then. It's sitting right there. So 1 g of force would be 1 mg equaling 4 pi squared mr over t squared. Masses cancel out. Time pops up here. 4 pi squared. I said I was going to make this thing a radius of 40 meters. Over, I'm going to get my g in there. So t would be approximately 4 times pi squared. It's 39.4 times 40. It's 1,579 divided by 9.8 gives me 161.136 seconds. Seconds squared, sorry. So I'm going to have to square root that. Gives me 12.694 seconds. Okay, so we should turn that into a speed. Speed is distance over time. If you're not accelerating, should be 2 pi radius over the time. Should be 2 pi 40 meters over 12.694 seconds. Let's put that in the denominator. Times 2 times pi times 40. 19.798, 19.799 meters per second. Okay. Multiply by 3.6 would give me kilometers per hour, and I end up with 71.276. So if you could build this thing, and then you could get it spinning so that it completed one full rotation every 12.694 seconds, which means the edge is traveling at about 71 kilometers per hour, then you would have built a habitat that is 80 meters wide, where people would live on the outer circumference as it spun and experience Earth's the same downward pull as Earth's gravity provides. Now you could make that thing as long as you want, right, as it spins this way. So if you needed more space, you just make it bigger. If you feel you've run out of space, then you just add another module and get it spinning and then weld the two together while they're freely rotating in space. It's not a crazy idea. It's a simple idea with some complicated engineering ramifications, which seems to be the theme song for physics. And they're like, I got this crazy idea, and the engineers say, no, don't do that. But it is fun to think about. So if you scroll down past the video, there's like a diagram of a complicated rotating space tube base that might amuse you to read through. And then there's some problem sets that are just going to ask you some more questions about centripetal motion, about trying to increase the radius or decrease the radius or calculate the simulated gravity, etc.